Hey, what's up? Okay, this is chapter 3.3, page 123, question number 2. A curved road with a radius of 450 meters in the horizontal plane is banked so that the cars can safely navigate the curve. Calculate the banking angle, so that's what we're looking for, the angle, for the road that will allow a car traveling at 97 kilometers per hour to make it safely around the curve when the road is covered with black ice. So we're assuming no friction. So the car is traveling at 97 kilometers per hour. Convert that to meters per second. Did I do that right? Yes, okay. So our speed is going to be 97. A shortcut is just 97 divided by 3.6. Or you could do times 1000 divided by 3600, but it'll get us a speed of 27. I'm just going to say 26.94 meters per second. Okay, so the question is asking to calculate the banking angle that will allow cars to travel safely. So what we're going to need to do is, first let's draw what's happening. So here, unrealistic drawing, that's fine. Here's our car. Here's our force of gravity, and that's mg. And then here's our normal force. And yes, so this has a speed, this is our theta. This has a speed of 26.9 meters per second. So the first thing we have to do, first we can acknowledge that the y components, the sum of the y components will equal 0. This is our Fn, so let's call this Fn. Here's our theta, so it's the same inner theta as this one. So here this is Fn sine theta, this is Fn cos theta. So our sum of the forces in the y direction will equal 0. So Fn cos theta minus mg equals 0. Fn cos theta equals mg. Fn is equal to mg over cos theta. We're going to need this when we look at the sum of our forces in the x direction. So since the car is not moving up and down, and we know that the car is moving up and down, so the sum of the forces in the y direction is going to be 0, which means that if there's a net force, and we know there's a net force, it will be the x components. So the sum of the forces in the x component is really our F net. But first, let's look at what those forces are. So there's only one of them, and it is Fn sine theta, which is the x component of our Fn from over here. So this F net is our centripetal force. It's the force that's allowing for acceleration. Sorry, I'm a little all over the place. Okay, so our centripetal force is Fn sine theta. Now we know here that Fn is also equal to mg over cos theta, so we're going to sub that in. So mg over cos theta times sine theta. Sine theta over cos theta is the same thing as tan theta. So now we have mg tan theta. Now, we're looking for centripetal force. In order to find centripetal force, normally when we're doing force calculations, we do F net equals ma. Now, since we're doing centripetal force, we're doing Fc equals mac. The equation or equivalent for AC is v squared over r. So in order to calculate Fc, we just do mv squared over r. So we're going to plug that in over here, mv squared over r. And I'm pretty sure this is a formula that I know our teacher will probably give. I can't speak for anyone else. But it's a centripetal force equation. So here we have a mass on each side, and we don't have a mass. So this works out nicely for us because we can just cancel that out. Now, we do have every other value. We know that our speed is 26.94. So that's, I'm going to write 27. 27 squared over r. Our radius is 450 meters. Our force of gravity is always our g is always 9.8 times tan theta. Tan theta is a value we don't know. So what we can do is we can calculate this. So that's our 27. So 27 squared divided by 450. So this is 1.61. And then this, we could divide by 9.8 and divide by 9.8. And that'll get us just tan theta. So this value, if we divide it by 9.8, is 0.1646. So, I'm going to write 165. So that's what we've gotten is equal to tan theta. To get theta by itself, we inverse tan. So now theta is equal to tan inverse 0.165, which will give us a theta of 3.348. I'm going to write, 9.348. 9.35 degrees. And there you go. See ya.